When astronomers point their telescopes into deep space and watch galaxies spinning slowly in the darkness, they are observing one of the most fascinating mysteries in modern science. A galaxy is not a solid object like a planet or star, but an enormous gravitational system made up of billions or even trillions of stars, clouds of gas and dust, and invisible forces that stretch across hundreds of thousands of light years. For decades, scientists assumed that the visible material in galaxies, the glowing stars and nebulae we can detect through telescopes, should account for nearly all of the gravitational pull that holds these cosmic structures together. But when researchers began measuring how galaxies actually rotate, the numbers did not add up. The outer edges of galaxies were moving far too quickly to be held in place by the gravity of the stars we could see. According to the laws of physics, those outer stars should have been flung into intergalactic space long ago. Instead, galaxies remained intact, spinning gracefully like giant cosmic pinwheels. Something invisible was providing additional gravity, something that did not emit light, reflect light, or interact with telescopes in any direct way. This mysterious substance came to be known as dark matter, not because scientists could see it, but because they could infer its presence through the gravitational effects it produced. The discovery fundamentally changed how we understand the universe because it suggested that the visible matter we observe, everything from stars and planets to gas clouds and galaxies, accounts for only a small fraction of the total mass that exists. Modern estimates indicate that ordinary matter makes up roughly 5% of the universe. The rest consists mostly of dark matter and another even stranger component known as dark energy. Dark matter alone appears to account for about 27% of the cosmos, meaning the structures we see are essentially embedded within enormous halos of invisible mass that extend far beyond the glowing boundaries of galaxies. One of the earliest and most convincing pieces of evidence for dark matter came from the work of astronomer Vera Rubin in the 1970s. Rubin studied the rotation curves of spiral galaxies, which describe how the orbital speed of stars changes depending on their distance from the galactic center. In our solar system, planets farther from the sun move more slowly because gravity weakens with distance. Scientists initially expected galaxies to behave in a similar way, with stars at the edges orbiting more slowly than those near the dense central core. Instead, Rubin found that stars at the outer edges were moving just as fast as those closer to the center. This meant that the mass responsible for the gravitational pull was not concentrated only where the stars were visible. Instead, galaxies appeared to be surrounded by massive halos of unseen matter extending far beyond the luminous disk. Further evidence emerged from studies of galaxy clusters, which are massive groupings of hundreds or even thousands of galaxies bound together by gravity. When astronomers calculated the gravitational mass needed to keep these clusters intact, they discovered that the visible galaxies and gas clouds accounted for only a fraction of the required mass. The clusters behaved as if they were embedded in enormous reservoirs of unseen material. One particularly dramatic example comes from observations of the Bullet Cluster, where two galaxy clusters collided and passed through each other. The hot gas clouds within the clusters collided and slowed down, producing bright X-ray emissions that telescopes could detect. But gravitational measurements revealed that most of the mass passed straight through the collision without interacting, separating from the visible gas. This behavior strongly suggested the presence of invisible matter that interacts primarily through gravity rather than through electromagnetic forces. Another method scientists use to measure the presence of dark matter is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. According to Einstein, massive objects warp the fabric of space-time around them, bending the path of light that passes nearby. When astronomers observe distant galaxies behind massive galaxy clusters, the light from those background galaxies becomes distorted, stretched, or magnified by the cluster's gravitational field. By analyzing these distortions, scientists can calculate the distribution of mass within the cluster. The results consistently reveal far more mass than can be accounted for by visible matter alone, providing additional confirmation that something unseen is contributing to the gravitational structure of the universe. Despite decades of research, scientists still do not know exactly what dark matter is made of. The leading hypothesis is that it consists of particles that rarely interact with ordinary matter except through gravity. These particles would be extremely difficult to detect because they would pass through normal matter almost entirely unnoticed. Experiments around the world have been designed to capture rare interactions between dark matter particles and atomic nuclei, using detectors placed deep underground to shield them from cosmic radiation. While several experiments have reported intriguing hints over the years, none have yet provided definitive proof of a specific dark matter particle. Another possibility is that dark matter could consist of exotic particles predicted by extensions of the standard model of particle physics. Candidates such as weakly interacting massive particles, or WIMPs, were once considered the most promising explanation. However, after years of searching without clear detection, researchers have begun exploring alternative ideas. Some theories propose ultralight particles known as axions, while others suggest dark matter could form massive compact objects such as primordial black holes created in the early universe. Each possibility carries unique implications for cosmology and particle physics, making the search for dark matter one of the most important scientific challenges of the century. Dark matter also plays a crucial role in the formation of galaxies themselves. Computer simulations of the early universe show that tiny fluctuations in the density of matter gradually grew under the influence of gravity. Dark matter, because it interacts weakly with radiation, could begin clumping together earlier than ordinary matter. These dense clumps acted as gravitational seeds that attracted gas and dust, eventually leading to the formation of stars and galaxies. Without dark matter providing this underlying structure, the universe might look very different, with far fewer galaxies and less organized cosmic structure. Large-scale maps of the universe reveal that galaxies are not distributed randomly, but instead form an enormous cosmic web of filaments and clusters separated by vast voids. Dark matter appears to define the skeleton of this structure. Ordinary matter gathers along these dark matter filaments, forming the luminous galaxies we can observe with telescopes. When astronomers simulate the growth of the universe using models that include dark matter, the resulting structures closely match what we see in deep sky surveys. This remarkable agreement provides additional indirect evidence that dark matter is a real and essential component of cosmic evolution. Modern telescopes and observatories continue to refine our understanding of dark matter through increasingly precise measurements. Instruments like the Hubble Space Telescope and large ground-based observatories have mapped the distribution of dark matter in distant galaxy clusters using gravitational lensing. Upcoming missions such as the Euclid Space Telescope and the Vera C. Rubin Observatory aim to survey billions of galaxies, providing detailed maps of cosmic structure that could reveal subtle clues about the nature of dark matter. By studying how galaxies cluster and evolve over billions of years, scientists hope to narrow down the possible properties of this invisible substance. The search for dark matter also intersects with research in particle physics. Massive particle accelerators such as the Large Hadron Collider attempt to recreate conditions similar to those just after the Big Bang, where exotic particles might be produced. If dark matter particles can be generated in high-energy collisions, they might reveal themselves through missing energy signatures in detector data. Although no definitive dark matter particle has been discovered yet, the ongoing experiments continue to push the boundaries of what is possible. Even though dark matter cannot be seen directly, its gravitational influence shapes the universe on every scale, from the rotation of individual galaxies to the distribution of massive galaxy clusters across billions of light years. The realization that most of the universe is made of something invisible challenges our intuitive understanding of reality and reminds us how much remains to be discovered. Every time astronomers observe a galaxy spinning faster than expected or detect light bending around an unseen mass, they are witnessing the subtle fingerprints of a hidden cosmic component that holds galaxies together. In many ways, dark matter represents one of the most profound scientific mysteries of our time, because it sits at the intersection of cosmology, astrophysics, and particle physics. Solving this puzzle would not only explain how galaxies remain stable, but also reveal new fundamental particles or physical laws that extend beyond our current understanding. Until then, Astronomers continue to map its presence indirectly, measuring the gravitational effects of something we cannot see but know must exist. The universe may appear filled with brilliant stars and glowing nebulae, but the true framework holding everything together is largely invisible, silently shaping the cosmic structures that stretch across the vastness of space. As astronomers continued to study the large-scale structure of the universe in more detail, they began to realize that dark matter was not just a mysterious extra ingredient sprinkled throughout galaxies, but rather the dominant framework that determines how matter organizes itself across cosmic distances. When scientists map the positions of millions of galaxies using massive sky surveys, the result is a breathtaking picture of the universe resembling a vast three-dimensional spiderweb. Galaxies gather along long filaments that stretch for hundreds of millions of light years, while enormous empty regions called cosmic voids lie between them. The reason this pattern forms appears to be the gravitational influence of dark matter, which clumped together first after the Big Bang and created the scaffolding on which visible matter eventually settled. In other words, the galaxies we see are essentially tracing out the hidden skeleton of dark matter structures that dominate the universe. The evidence for this cosmic scaffolding becomes even clearer when scientists examine the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation. This radiation is a nearly uniform glow that fills the entire universe and represents the moment when the cosmos cooled enough for light to travel freely through space. Sensitive satellites have measured tiny fluctuations in the temperature of this background radiation, revealing subtle variations in density that existed in the early universe. The stars and galaxies that fill the night sky may appear to be the main actors in the cosmic story, but in reality, they are only the luminous highlights of a much larger, unseen structure that binds everything together across billions of light years.